The final reaction in chapter 24 is called the Michael reaction, and it does the following: alkylates at the beta carbon. So let's explain what it says here. So the addition of an enolate to the double bond of an alpha beta unsaturated carbonyl, we've seen these before. It's called the Michael reaction, and this reaction works especially well when the enolate is a stabilized enolate. So this is very important. You have to have a stabilized enolate. And we're going to look at examples of these. We've already seen some, but again, we will see them. So stabilized enolate. And again, formed from a beta dicarbonyl compound. So once again, go back a few pages, and then you will see the beta dicarbonyl when we did the aldol and the clazen. But let's begin. So this is the reaction right here. You have an alpha beta unsaturated carbonyl, and you have what could potentially become an enolate. So let's show you the product of this first, and then we will show you the mechanism. Let's just redraw this a little bit here. So this is the product, and I will highlight both so you can get an idea of what exactly happened here. So and let's use green for the other one. Right here. Okay, so let's actually look at the mechanism. So we bring this compound so we have the CO2. And we have the two H's, and we're going to deprotonate from this base right here. Once again, nothing is new here. Charge and negative. So this is going to create the enolate for us, stabilized. And we're going to redraw this just like I did above. Okay, so this is drawn this way. You should be able to trace everything. So the CO2ET is, here's a C, carbonyl oxygen, and then the OET, ethoxy. So that's again drawn in a way to help us draw the mechanism more easily. So here's your mechanism. We've seen this before in chapter 20 when we talked about the organocopper reactions where they attack the alpha beta unsaturated carbonyl. And this is the mechanism. These lone pairs are going to attack at that carbon. So electrons are going to shift. Okay, and let's see what the product is so far in the next step. Okay, so you should be able to trace everything. So here's the bond that formed. I'm going to highlight the bond that formed between this carbon and that carbon. I'm going to put yellow on both. So here it is. This is the new bond that's formed between them. Now, there's one thing that I haven't finished here. So we have the movement of the electrons. And then finally, what happens is that this double bond gets protonated from the alcohol. And it yields the product that we described, and we have a name for it. Have to ensure that all arrows are there. So these come down, this attacks, and then you have your carbonyl. Sometimes they show them in different ways, in different processes, but we're all going to do it in one process just to accomplish that. So this is the product. Now, a few things before we move on. This is a 1,4 conjugate addition, or 1,4 addition, or basically a conjugate addition. So this is a 1,4. We're going to write this down here. It's a 1,4 addition. And that is between an enolate, a stabilized enolate, and alpha beta unsaturated carbonyl. Okay, so this is your alpha beta unsaturated carbonyl. Unsaturated means that there's a double bond, and this is your stabilized enolate. So we need to also get into the terminology of the Michael addition. So the stabilized enolate served as a nucleophile. So this is a nucleophile, but we have also a name for it. We usually call it a Michael donor. So donates a lone pair to form a bond, and this is obviously the electrophile. And we have a name for it. It's called a Michael acceptor. And what they form, the product, is what we call a 1,5 dicarbonyl. And the 1,5 is for the following reason. So watch the counting. 1, 2, 3, 4, and then 5. If you count also down this way, you have 5. So you have a 1,5 dicarbonyl. Either you go down or you go up. That's why it's called a 1,5 dicarbonyl. Dicarbonyls mean you have 2 carbonyls, one at 5 and one at 1. and either again on each side. So the electrophile, the alpha beta unsaturated carbonyl accepts a pair of electrons. That's why it's called a Michael acceptor. And the attacking nucleophile donates a pair of electrons. That's why it's called a Michael donor. Like I said, the product is a 1,5-dicarbonyl compound. Now, there is on this page a list of those are examples of Michael donors, and once again, those are stabilized enolates. You have to ensure you understand why they are stabilized. Stabilized enolates. And these are a list of Michael acceptors. Notice how they have the alpha, beta, unsaturated carbonyls. So they're all, they all satisfy this criteria. So here's the alpha, here's the beta, here's the alpha, here's the beta. So be aware again, this is an aldehyde, this is a ketone, this is an ester, this is an amide, a nitrile, a nitro. So you have all of these conjugated compounds that serve as that. And let's actually, in the next video, talk about how to predict or how to come up with what makes a final product, or what was the Michael donor or what was the Michael acceptor.